Dear students, the topic is length contraction and time dilation. That is the Lorentz transformation. The topic code is EMREL-5. The Lorentz transformation forms the basis of the special theory of relativity. The following are the few features of the Lorentz transformation. A. The Lorentz transformation reduces to the Galilean transformation if we set the velocity of the object v very small as compared to the speed of light. That is, v over c is very small, equal to 0, negligible. Then v is very small, they are smaller than the c. The relative velocity v of the two systems cannot be greater than c. That is v, and otherwise x, y, z, t become imaginary in one system or the other. The C feature is that there are really 4 independent equations. The relation between the quantities in one frame and the corresponding quantities in the other frame can always be expressed by either one of the two equations which are equivalent. That is, right hand side can be deduced from the left hand side. For example, in reference frame 1, these are the equations. Reference frame 2, these are the equations. x1 is equal to gamma x2 plus v times t2, and y1 is equal to y2, z1 is equal to z2, t1 is equal to gamma t2 plus v by c square into x2. In reference frame 2, x2 is equal to gamma x1 times x1 minus v t1 whole bracket, v2 y2 is equal to y2 is equal to y1, the y2 is equal to y1, z2 is equal to z1, t2 is equal to gamma times t1 minus v by c square times x1 whole bracket. Now the third feature, we can express that the coordinate system in RF1 by looking at these comparison, that in RF1 is identical to the coordinate system in RF2, except that the subscripts 1 and 2 are interchanged, and that plus v, the positive velocity, is substituted with the negative minus v. So this is a general rule. Now we express that this is termed as a general rule, that if a quantity in one reference frame is known in terms of the quantity in other frame, the inverse, that is opposite relation, in here means opposite relation, is obtained by interchanging the subscripts 1 and 2. We will change the subscript 1. If it is in 1, we will replace it with 2. If it is in 2, it will replace it with 1, and changing the sign of v. If it is positive, then it will be negative. If it is negative, then it will be positive. So this is a general rule we define regarding the two reference frames that are being expressed as the general rule. Now let's now take the transformation of length. That's we call length contraction. Now let us consider two frame of references, S prime. Here we have, this is the S and this is the S prime. Let me little bit make it smaller. Okay, so consider two frame of references S prime, but this will not be visible for you, so I make it more zoomed. So when S, which is a function of x, y, z coordinates, reference frame 1 is stationary, where the S is stationary, and S prime x, which is having coordinate x prime, y prime, z prime, reference frame 2 is moving with the uniform velocity v along the positive x direction. So let a meter rod AB is placed in S prime. Here, this is the meter rod. Observer O prime is observing the length to be the L naught. This is the proper length, and L is the length observed by the observer in this S, the frame of reference S, which is stationary, and this is moving with the constant velocity. So let's see, with its proper length L naught, the AB is the proper length, AB meter rod, which has a L naught proper length, The same meteoroid is observed by the observer in reference frame 1 as the S reference frame as AB, but with the length now L. Now let the position of the points A and B in S prime are given as the E x1 prime, y1 prime, z1 prime, t, and the x b and b is x2 prime, y2 prime, z2 prime times t. We take the times is a simultaneous, that is at the same time both observer observe that length, which is the t prime is equal to t1 or t2 or whatever you can see, both observer times. So that is the time is same when the event occur. The change in the position is along x-axis only, while along x-axis only, no change along y and z. So while the along other coordinates we have no change, that is the y1 is equal to y1 prime and so on and so forth along z and other z and y2 and z2. Now let us consider that the length of the rod observed by the observer O in the reference frame S prime is given by L naught is equal to x2 minus x1, and let the length in the observed by the observer in S frame L is equal to x2 minus x1. So from the Lorentz transformation of space coordinates, we have x1 now prime will be equal to x1 minus x vt divided by 1 minus v square by c square. So v and t are taken to be, the v is constant and t is also the common to both. x2 prime is equal to x2 minus vt minus vt divided by 1 minus v square by c square square root. Now subtracting expression 3 and 4, we have the x2 minus x1 prime is equal to x2 minus vt x minus x1 plus vt. So vt will cancel out. So what we get, x2 minus x1 prime is equal to x2 minus x1 over 1 minus v square by c square, where the x2 minus x1 x2 prime minus x1 prime is the L naught, which is the proper length, and x2 minus x1 is the length L, which is observed by the observer, stationary observer in the reference frame S. So L naught is equal to L over L 1 minus v square by c square square root, or L is equal to L naught times 1 minus v square by c square, or L is equal to L naught over gamma. This is the, which gamma is equal to 1 minus v square by c square square root. This is the invert. If we invert it, then we get 1 over L. So 1 over L is equal to sorry, in this case is the gamma. L is equal to 1 over gamma, or gamma is equal to, in this case we take the inverted this 1 over that L is equal to L naught over gamma. Hence the length of the meteoroid observed by the observer in S reference frame will be seen as contracted or shortened. Hence the length contraction is observed in relativistic level whenever things move with the relative velocities to the speed of light. The second consequence of this relativity is that the transformation of time, that is the time dilation. Let us consider a rocket with a reference frame S prime having two mirrors, M1 and M2 mirrors mounted at the at the floor and at the roof. A light pulse originates from M1, is reflected back from M2, traveling with a distance d. These are two mirrors, M1 and M2. So this is the d distance between the two mirrors. Observer O prime is the S prime reference frame 2 is observing this whole the event. Now the traveling distance is twice as seen by the observer O prime. So it goes one way 1d and then comes back 2d. So here is the other observer, stationary observer outside, observing the same event taking place. One when it is stationary, they are coinciding. This is with if a smaller velocity, then obviously the same distance will be traveled as observed by the O prime. But if it is moving with a velocity v, which is relativistic velocity, we will see that that will be a different situation then. So what we have, while the observer O is watching this event taking place in reference frame 1 or S, let the both observer O prime have the synchronized clocks recording the time delta t and delta t naught respectively. So let the reference frame 2 is moving with a uniform velocity v, and observer O prime observes that during the delta t naught time that the light travels 2d distance between m1 and m2 mirrors. Now the velocity observed by the observer delta t naught is 2d by c. So this is the observer. We'll see O prime observer, that is in the reference frame 2. So that's equation number 1. Now while the observer O in reference frame 1 observes that delta t is equal to 2L by v, the light travels longer distance given as c is equal to total distance divided by total time, to total distance 2d divided by delta t. So what this observer sees, that when the light pulse starts moving from the mirror 1, since along with that this vehicle is also moving with velocity v, which is a relativistic velocity, then what this observer sees, that this pulse is moving this much distance till here, and then reaches to the top, and then comes back. Along with that, this vehicle is also moving, or the rocket is moving, and then when it reaches back to the floor, it travels extra this d plus d, which is 2d, because this is the velocity v is moving with the velocity v. So let L be the distance from the center to the start here, initial distance, and then at the center, and then the final distance. So let L be the distance here, and d be the hypotenuse. It's a right angle triangle, we can see. So d is given by this is the L square plus d square root, this d distance. So this is 2d, okay. So and the vt is the v times t, which is a 2L. This is L plus L. 2L is equal to v times delta t. So that's how the delta t is equal to 2d. This one delta t is 2L by v. So putting these respective values, that is the value of d, which is L square plus d square root here, so which is given by 2 into L square plus d square root by delta t. Also, since L is equal to v delta t by 2, so putting again the respective values, what we get, c is equal to now this term, which is the v square delta t square by 4 minus delta t naught square c square by 4. Further squaring the both sides and rearranging and simplifying, what we get in the end, that we get delta t over delta t naught is equal to 1 over 1 minus v square by c square root, or delta t is equal to delta t naught over 1 minus v square by c square, or which is equal to gamma times delta t naught. This was the proper time. Now this is the observed time of the observer outside watching the event, and he she found that this time is dilated. Gamma factor is multiplied with that proper time, so it shows that its clock as the longer time that observer will see, which is stationary outside, observing the whole phenomena. So this event is called the time dilation. So that is the end of the topic. With this we reach to the end. Thank you.